Okay, so well, the third class, right? So in the past 2.5 classes, we've learned about CUDA, specifically about how CUDA works, what are the paradigms, the keywords, the types of functions we can run. In the next whatever hour or so, what we're going to do is take a step back and see how the whole programmable GPU came into being, but what were some of the first steps and how that has influenced what CUDA looks like today. All right, so some acknowledgements of previous students and GPU slides. I found this image to be really awesome. I think, and Microsoft posted this probably a couple of years ago about them digging through all the GPUs and what were then not even called GPUs out of their driver toolbox kits and then putting them on a wall with the entire timeline. It was really fantastic to see. So you can check out that blog on that link below. All right, so let's talk about how CPUs and GPUs are different and how they do different things really well. So in some keywords here, so flops are floating point operations. These are your addition or multiplication operations. Gigaflops is 10 power 9. Teraflops is 1,000 gigaflops, which is 10 power 12. Flops are not a perfect measurement of performance. You're going to have different factors: memory access, latency, caching. All of those things are going to influence how many flops you get in the code that you write and on the chips that you're working with. It's definitely idealistic when NVIDIA or Intel says this hardware can get 10 teraflops. It's definitely an ideal number, but you can get close to it, but not completely. So that's just something to keep in mind. So if you discuss flops, that's a way of indicating the performance we hope to achieve rather than trying to completely match the number that we see. So these GPUs, and I know there are newer versions of these. The AMD Ryzen 3900X was 1.55 teraflops. Intel's 19 was 1.22 teraflops. How much was an RTX GPU? Anybody remember? Anyone? Pick your favorite. Yeah, so the Titan RTX, the first RTX released, was 16.32 teraflops. That is about 12 times, 13 times more than what Intel or AMD played on their CPUs. And then for those of you interested in autonomous driving, the Drive PX2 that NVIDIA uses for their autonomous driving cards, that's up to 7.5 teraflops. It has 2 GPUs and 2 tegra-cores on it. So that gives it that much performance. Again, the trend, if we look at it as a chart about how performance is increasing, the NVIDIA line for GPUs, and this sort of relates to the AMD line as well. I'm just using an NVIDIA chart. Is it's growing up exponentially. It's growing up really fast. Whereas the Intel lines down here are much more linear, and you could say are probably hitting Moore's law today. So that's compute. Looking at bandwidth, this has also been increasing. So if you look at the green lines, which are our GeForce and Tesla GPUs, those are accelerating as they increase. With things like DDR5 and high bandwidth memory, all of those things are increasing. Whereas the Intel one, with Intel is going to read your DDR3, DDR4 RAM, right? So that's on a much lower level. It's much slower. So basically, that all that goes to say is GPUs have both faster bandwidth and more compute capability, and you want to take advantage of that. Whereas CPUs, and we see these in the next year's slides, is much more general purpose. So what becomes important and what these companies try to advertise is how they're the best in one of these things. You can, performance is not just raw performance, right? Yeah, and in one way you can say a Ferrari goes 200 miles an hour. Yeah, SpaceX rocket goes whatever, how many kilometers per second. So performance is relative to what you want to do. If you wanted to do the best graphics game, no budget limited, yeah, you're going to pick one of the big RTX GPUs. But you couldn't mount that on a drone to do machine learning analysis or visual analysis for object detection. You have to pick one of the Tegra cards because it has to run on a battery and needs to have good performance per watt. That becomes important. So it really depends on what you want to focus on here, the performance you need and what you want to focus on. So that's like an overview of how we are going to judge performance. Okay, so let's look at a CPU. Who can tell me what the core components of a CPU are? And trust me, I'm no expert. You do that. Some of you have probably taken the architecture course here, so you probably know. Go ahead, just shout it out. What else? The cache. What else? Registers. ALU. Okay. Sorry. Decoder. Yeah. Okay. I think that's a good start. So looking at a few desktop applications, and these are very basic. I know Vim and LS are probably the simplest applications that we will think of. One thing you'll notice in some of the basic applications, we're not talking about gaming or Photoshop or video processing just yet. We're talking about the basic ones that all of these big applications build on. Just comparing Vim and LS, and these were tested in at NEI. What they have is they're generally single-threaded. They have lots of branches because they have to determine what you're doing with every click. And they have lots of memory access, cache, RAM, etc. So just comparing how much performance is needed for these applications, you're in conditional branches, if, else, while loops, for loops, all of those things, about 12 to 13%. You're accessing memory almost half the time. What did we try to do with matrix multiply? We reduced how much memory we were using. And then vector instructions, which is simply single instruction, multiple data, is almost non-existent. So and these kind of applications really highlight the key differences between GPUs. On CPUs, conditional branches and memory access are not bottlenecks, or not considered bottlenecks. Whereas on GPUs, they definitely would be. So, not to insult anybody, who's an expert at computer architecture, but this is what a simple CPU code would be and would do. It fetches the instruction, decodes the instruction, executes it, reads the memory, and then writes it back. Right? Just a few keywords here, just so that for those of you who may not have taken computer architecture, PC is program counter. So this is sort of your, if you were counting lines, I dollar is your instruction set. Registers S1, S2, and D are your registers. And then D dollar is your output memory. Okay. So all these and or diagrams that you see here are generally representative. But what you need to remember is this line down here, which is what we're going to do. And so this takes all of these steps occur in one clock cycle, right? So in one clock cycle, you do these. And then what we see here is that it's generally bound by what path the data is. And by that, what I mean is these arrows that are representatively drawn are essentially connecting different logic. The add logic, add two numbers is going to be different from subtract, is going to be different from divide, and so on and so on. So what we execute here, or how the data flows, is completely dependent on the operation. If we divide this up, so you're getting memory access here on a, if we can call it instruction level patterns. What we can do is you can P here means fine. So you can get the program counter in one cycle, the register file in another cycle. You can divide up the AMU so the compute is happening in another cycle, and the data memory and the output is happening in other cycles. So what we've done here is essentially significantly reduce the clock period, but increase how many instructions can run at the same time. So if you think of this as a queue, if Pn is here, Pn minus 1 is going to do this, Pn minus 2 is going to do that, Pn minus 3 is going to do that. So you can have multiple instructions running at the same time. However, there's one bad thing here. Because of all these red barriers that we've created, you're going to get more latency. Because if the red file clock is taking more time, the instruction is going to wait because it can't go on to the next step. So what we have essentially done here is added the ability to run more at the same time, but increase latency. Now there are two questions here that may or may not be effective. One is what happens if there are dependent instructions? If one instruction that is maybe in the red file stage, but the next instruction depends on the result of that instruction. That instruction would essentially have to go all the way to the end, complete, before this instruction that might be here can go to the next step. So that can increase latency even more. And then the other thing that you have to remember is branches. If a branch happens where you're checking if else, then that's going to throw it off much more, because then you don't know which program counter to get and stuff until you've evaluated your entire result. So just because we've broken this up into stages and can run multiple at the same time doesn't mean it's the most often. The other thing I'll highlight here for comparison is a Go2 core, which is what, maybe 10 years old at this point, had 14 of these stages. So imagine having 14 red lines, but it's also a much complicated core, right? The Pentium 4s have about 20 stages, and then the modern CPU cores have somewhere in the middle. So this kind of pipelining, where you have multiple stages, allows for much higher clock speeds, because you can say that you're running them in a pipeline and you can run them in parallel. All right. So let's see how branches work in this. And feel free to make me slow down. This is all architecture stuff, which I'm using to explain how we come to GPUs, but feel free to make me stop there. If we have a branch, for example, in this J equal loop, where we are testing equality, you don't know what instruction to load in this first cycle until the result of this gets written out. So you see this loop here, this loop until this equal execution finishes, transfer into the result. The instruction here doesn't know which one is. So that causes a lot of stalls and latencies. And also, how many of you heard? Actually, let me go to the next slide. So this kind of branch prediction, modern CPUs do it really well. They like your modern CPUs are going to get about 90% accuracy because they can tell with the help of the compiler whether you're for I equals 0, I less than n, what is the majority branch prediction on that. So if you have a simple for loop like that, I equals 0, I less than n, I plus plus, the compiler will all the time predict that it's going to be true until it's false. Because the cost of being wrong is much smaller than the amount of time saved by being correct n number of times without having to check if I is actually less than n. If I is indeed greater than n, it's going to go and fix it and throw away a bunch of data, like prefetching and stuff. But the reason CPUs are good is because they do this really well, this model prediction of 90, greater than 90% accuracy. They raise the performance and efficiency of general purpose, programs that have lots of if-else, lots of for loops and things like that. The disadvantages are that it increases how many transistors you need on the chip. Because again, we are talking down to the metal, right? So we have to think in terms of transistors. The amount of transistors you need to be good at this on the hardware level significantly increases to mean that it actually takes up a chunk of the chip, which we'll get to in a bit. It also increases the fetch stage latency, because if you get something wrong, then you have to go fix all of it backwards. Okay. Now, what about security concerns? How many of you heard of Spectre and Meltdown? Probably 3-4 years ago, right? That's essentially this problem here. Spectre and Meltdown happened because of these issues. I'm no security expert, but the way I understand it is because, let's take our example of for I equals 0, I less than n. Okay. If you do it continuously, I'm assuming the CPU always executes it as true even beyond n, you could make it do other things that shouldn't be allowed at the hardware level. So you could access memory that should not be accessed by the program, bypassing all types of security. So it was a hardware issue, not a software issue. And that's why it was so difficult to fix and cause so much controversy. Okay. Any questions so far on branch connection? Okay. So let's look at memory. Basically, the crux is that the larger it gets, the slower it gets. This is true on the GPU as well. So rough numbers, your SRAM here, which is cache on the chip, is going to have hundreds to thousands of gigabytes of speed and very, very short latency. But it's also very small in size. We get about 20 megabytes for the entire host chip. These are not GPU numbers, these are CPU numbers. Your RAM, you have 1632, 64 GB in your laptops. That has a slightly higher latency and a much slower speed. So you're getting at least 10 times, if not more, slower bandwidth on your RAM. Then you get into SSDs, which are much faster. I need to update the slide. NVMe SSDs are, you can get multiple thousand megabytes per second. That's using the PCIe bus, of course. And then if you get on back to spinning hard disk drives, you're getting about 100 megabytes and at a much longer latency. So we are literally talking about milliseconds now, not nanoseconds. But you increase the size. So what is caching and why? So caching both on the CPU and the GPU is used to keep data that you need close to the chip, right? For example, if you were taking a new job and you didn't want to have a car, you would probably take an apartment or something close to your job so that you reduce your commute. In the same way, if you're doing something over and over again in the computer, you're going to want to keep that data very near to the chip because so that you can use it much faster. So you can exploit both temporal locality, which means, for example, if you're using a loop and you're accessing the same data, you use it again. And then in spatial locality, because you know in that for loop, you're going to use one element and then the next element, your computer can be smart enough to know that, okay, this guy is using this memory sequentially, so I'm going to grab the next n chunks and put it in cache already, so that I don't even have to go to the memory next time. So you can do both. So from a hierarchy perspective, what you have is registers being the fastest and closest to the chip. Then you have your L2 cache and L3 cache. Then you have your main memory, which is generally RAM, and then you have the disk. Sometimes L3 may or may not be on the chip. And by that, what I mean is when you see the silicon die, the L3 cache may be kept off the chip, but somewhere close to it. So that way, you can make the size bigger with a lower latency. So it could help certain chips get fast. Now let's look at this chip. This is a Core i7-3960X from the Sandy Bridge architecture, which I believe was 2014 or 2015. It had 15 MB of L3 cache. Okay. And it had a 4-channel memory controller to give you 51 gigabytes per second of total bandwidth. But if you look at this is how it's actually divided up. Look at the percentage of cores, and these are disabled because you remember how I said they can be used in dimming and stuff. The percentage of the chip used for cores is way smaller than firstly the L3 cache, and secondly, the memory controller. So look at, from a percentage perspective, look at how much Intel is optimizing memory over compute to make sure that these chips can perform at the level that consumers expect. What the other thing I'll point out here is you don't see L1 and L2 cache, like I said here. It's not on chip. So L1 and L2 cache is essentially within the core itself, whereas L3 is outside the core and shared. So that's why you can have a bigger L3 cache. All right, let's compare that to a newer CPU. So this is the Coffee Bean CPU, which was the i9900 series, which I think is a year and a half kind of old, 8 cores, 2-channel memory, 40 gigabytes of bandwidth. So this has both 8 cores of CPU and also 24 GPU units. So EU is execution units. Let's look at how this was divided up. So look at how Intel changed the architecture from having this big L3 cache in the middle to having more space for core, a lot more for the GPU, and then divided up the L3 into multiple bits, and then added these ring, sort of, if you want to call circular agents or something between them. So that's how when you think of Intel's architecture and how they're making these changes over and over, they make these kind of optimizations where they're improving how the core size is versus how the cache is versus how the GPU is and all that. Okay. So coming back to, now we've seen CPU, right? We've seen how we add pipelines, we add stages, and then how that can impact performance, clock cycles, and things like that. Now let's start getting slowly into how decades worth of CPU design influence GPUs. Okay? So we saw the old pipeline, right? Where you had fetch, decode, execute, memory, right? What if you add another one of those pipelines? So now you can do the same instruction for multiple data. Okay, you'll start seeing a trend. So for example, consider this instruction cycle. You're doing an XOR operation on R1 and R2. You're adding R3 with R4. So just between these two lines, what can you tell me? Between the XOR and the AND. I know this is assembly, but because you're going back many, many years to understand. Yeah, yes, exactly. So because the addition R3 depends on what XOR writes to R3, you have to execute them in order. So let's look at sub R5, R2. So you're subtracting R5, R2 and writing the result in R3. And then finally, you're doing add increment or add integer, I think it's called, R3, 1 and storing that in R1. So essentially what we're doing is three things here. We have an add that is dependent on XOR because it is read after write. So the result of R3 or the result of XOR is required for add. The subtraction and add I are dependent again because of the same read after write. So you have to execute sub before add I. But this XOR and this sub are completely independent. So what if we change this a little bit? Okay, you might be thinking, oh, but R3 here, are we getting into a race number? Okay, but what if we wrote it up like this? Same set of instructions. P1, P2 write to P6, P6 gets read here. Then in subtraction, we write it to P8 and P8 gets read here. So we are no longer in that R3 conflict, right? So now XOR and sub can execute in parallel. So you can execute the first two lines sequentially, the last two lines sequentially, but these two and these two can be executed in parallel. They don't depend on each other. So by changing the registers they're writing, again, you don't do this when you're writing your C++ programs, the compiler and the runtime do this, but it's good to understand what goes on. So this is called out-of-order execution, where the compiler and the runtime are going to make decisions based on the programs you've written to reorder instructions for the benefit of performance. So they add this reorder buffer here, essentially, which allows them to reorder in-flight instructions so that you can add parallelism. And then you also add a scheduler so that it's able to control what things are getting scheduled and what not. So this essentially is the fetch and decode logic is always executing because it needs to know what the instruction is, what data it depends on. But because it doesn't get executed right away, it can get swapped out if needed. So once we've spoken about out-of-order execution, how do we get the parallelism of the CPU? How does Intel go from 1 core to 8 cores, 16 threads, 32 threads, whatever? How do they get there? So the first is instruction level parallelism, which we just spoke about. So uh, this out of order execution and this diagram essentially add instruction level parallelism. So what you get there is superscalar, where you're doing SIMD kind of instructions. Okay, you're doing the same operation on multiple data. You also get out of order execution, so that you're increasing the parallelism. Then you have data level parallelism, which is doing the same operation on an entire vector. And then you have third level parallelism, which is your 16 threads that you have on the CPU, which basically are completely independent pipelines that can run on the CPU without having to talk to each other. So those are generally the three high-level parallelism that you can get. So let's look at an example. Simple for loop, adding two vectors. Okay. In CPU data level parallelism, what we could essentially do is break it up so that our counter increases by 4. The number of lines we write increases by 4. But then what you could potentially do is if you make the execution unit, the ALU unit really wide, and I use the term wide loosely, you can execute all of these 4 lines in one cycle, right? So the number of loops you have to go through decreases by 4. The number of clock cycles you use decreased by 4. If all of these could execute at the same time. So this is exactly what happens when you do vector instructions on the CPU. If you've heard of these terms, SSE2 and ADX, these are those kind of vector instructions that allow you to work on multiple data, same instruction, and get you that parallelism that you need. Any questions so far? I know this is a lot of theory, very different from what we've done in the first 2 classes, but we'll get there and you'll see why I walked you through all the CPU architecture. Yeah, AVX is the new one. Yeah. Any other questions here? Okay. And then in thread level parallelism, what you get is basically the CPU deciding, or the user deciding how many threads to launch. So if you've ever done STD thread, new thread kind of thing, you are creating new threads to do operations independently or communicate between threads, right? And these are generally programmer controlled. So if you are writing P thread or STD thread, you are creating and destroying these threads so that they run on separate cores. And then you have simultaneous multithreading, which essentially you're scheduling instructions from multiple threads and using the reorder buffer. So ROB is reorder buffer. So you're using that so that you can make sure that multiple threads can run the same program without having to make sure they're not getting into race conditions. The advantage of this is that there's minimal hardware duplication because you're using the same thing in simultaneous multi-threading. It also allows more freedom for the CPU to do out-of-order execution, where you're changing the buffers around. But the downside is that because all of that context needs to stay live in the cache, you're going to spend more time switching context around, which can become costly on the CPU. Or use more resources because there's stalls and other operations. And then we get to multi-core, right? So this is where we are today, where you have these chips with 8 cores, 12 cores. What they essentially do is they replicate the entire chip. So you remember the Intel diagrams that we saw? We have the entire chips independent of each other. So that's multi-core here. So where you have the full pipeline, the memory, the cache, the buses are all replicated. But because of that, the utilization decreases because they're now separated from each other. And the only way to talk to each other is using that LT cache. So it becomes slower to communicate between the cores. But it has become a way to take advantage of Moore's law. Instead of finding a physical way of getting around Moore's law, with added cores and stuff to increase performance. So the conclusions on CPU side are that CPUs are optimized for sequential programming. This is your regular day-to-day programs filled with if-else, while loops, general day-to-day programming. They're designed, the hardware is designed to be good at pipelining, branch prediction, superscalar operations, out-of-order execution, so that the CPU can take more control of a programmer's code and execute in a way that is optimized to run on that CPU. They reduce execution time by high clock speeds and high utilization. But slow memory is a problem. We saw how RAM and cache on a CPU chip are much slower compared to how much core size they use. So a standard CPU, 8 or 12 active threads. I think the Intel 11 series has up to 24 threads or 32 threads, which is great. But how do you get to 32,000 threads or 100,000 threads? So by the way, I use 32,000 here because that's how many threads GTX 980 program. So coming back to how CPUs inspire GPUs, how did this happen? How did we go from CPUs going in a linear thing to GPUs exploding there? So let's see how we got there. So what are the graphics workloads? What was a GPU designed to do? If you go back to the roots, the purpose of a GPU, at least in the early days, and even today to a strong extent, is working on triangles and working on pixels, right? That's essentially what most of us use it for. And then early 90s, this is pre-GPUs days, Wolfenstein 3D and Doom. So this was 92 and that was 93, close to each other. These are all software rendered. There was no dedicated hardware for this. These games were written completely in software. So no GPUs. Wolf 3D was a 2.5D game. So it had the experience of that, but it's really, there's no ceiling. It looks big, but there's no ceiling. There's no changes in the floor height, so you're not going up and down, right? You're in a flat floor kind of thing. Yeah? There's no rolling walls either. See how Doom added some walls at least. There's no walls here that walk with you. The other thing to note is how the enemies always face the gamer. They're using sprites. They don't turn, or they turn 180 degrees at most. And then they use raycasting for shooting the bullet out. So you're shooting a bullet, a raycast into the scene to see which enemy you hit. Doom was based on DSP3. So, well, those of you who've taken data structure classes have probably learned of DSP3. That's what is done here. And they added texture mapping to all the surfaces. So that's why you see the ground has some texture, the walls have some textures. Whereas in Wolf, you only had the walls that were textures, the floors were just either plain gray or some procedural stuff there. But it also had some level of lighting, shadows, and stuff like that. All right, so that's early 90s. So why GPUs? graphics workloads, like we saw, which are pixels and triangles, are embarrassingly parallel. If you're doing one operation on one pixel, you're very likely doing it on every pixel or on many, many pixels at least. Similarly, if you're applying a transformation to your triangles, you're applying that same transformation to all the triangles. So this is what we call embarrassingly parallel, both in the data parallel and the Python parallel, because you can execute them at the same time. Then CPUs and GPUs, because they're their own processing, will execute in parallel. And then within hardware, you can have texture filtering, rasterization, and stuff, which need to be really fast. So remember how in the earlier classes I said anything that's done in hardware will be faster than being programmable. So the raster engine here, the texture filtering, doesn't have to be programmable. There are very specific operations that can happen. So making it fixed function in the hardware will speed things up. Of course, you get some level of options and controls on what to do, but generally the entire pipeline is implemented in hardware. So beyond graphics, what else can we do? Some work that you may have done in your various classes are plot simulation, particle simulation, matrix multiply. That's definitely on the data parallel side. All right, so let's look at some shaders. I hope everybody's at least seen one shader so far, having taken 5 seconds. All right. So what we are looking at here is a simple diffuse reflectance shader, right? Something you've probably all written a version of in 560, where you take a function and apply to all the pixels. Why does that sound familiar? Because we do similarly in CUDA, right? So you want to apply this to millions and millions of pixels, but there is no for loop yet, right? So the parallelism is implicit. So once you compile the shader, what happens is that it gets coded into assembly language, which the CPU can understand. And then each of these is going to read one pixel and write out one pixel. Okay. So in the shader, you're going to have the fetch decode, you're going to have an ALU, and the execution context is essentially your registers and your cache. So you're going to go on this line by line, execute the shader for each pixel. Now, in the CPU, in the pre-multi-core era, so this is the Doom and the Wolfenstein and stuff. And we saw this with the Intel chips as well, right? So you have fetch, ALU, and execute. So if we draw a box around these, that's essentially your core. Along with the branch predictor, memory prefetcher, out of order execution, all of that is on the core today. So this L shape is on the core. That big data cache is outside the core on the CPUs, so that it can store more context and do switching easily that way. Now, what if you take that CPU design that we had in this slide, okay, and you increase the transistor count to increase the number of parallel processes that you can do? Okay, so instead of increasing memory or something, instead of making your data cache bigger, what if you use the same transistors to add another pipeline? So something like this, right? So now you have 2 cores which can process 2 units independently. So now you have 2-way parallelism. So 2 cores. Okay. Why stop there? If you can do 2, you can do 4. Now you have 4-way parallelism. Isn't this what we've seen growing up with Intel cores, 4 core, 6 core, 8 core, similarly? Why stop at 4 when we can go to 16, right? or why stop at any number when you keep going on? Okay, but at some point you're going to have to stop because you don't have enough transistors. The key thing here to remember is that when you have this shader here, all of these units, all of our 16 units are executing the same thing, except on different units. So the instruction that all the 16 cores are getting is the same, except the data is different. So you take that simple core and you change it up. What are some ideas that we have to change it up here based on what I just said? So you have a lot of data. You have the same instructions. How should we change this? Remove the B code. Okay. How, that is one way to answer it, but you need some fetch and decode, right? Because you still have to get the instruction. What is another way to think about it? That is getting towards right answer. What is another way to think about it? Yeah. Very good. So what is it? We keep the fetch and decode the same because we still need to pull our instructions, right? But we divide up our ALUs to be much smaller, and we divide up our execution context to be much smaller and per ALU. Okay. So this way you're changing the cost complexity of your core. So instead of adding these many cores or duplicating all the resources, what if we change the idea to be, okay, let's keep the fetch and decode the same, but change how ALUs are different. Okay? So now what you can do is take that same shader, allow it to do vector operations, so you can see this vector. Now you have, instead of doing 1 pixel in, 1 pixel out, you can do 8 pixels in, 8 pixels out. Everybody following me here? What will we do? What shall we do from here? How shall we optimize this more? I'm not saying go from 8 to 32 or whatever, but how do we take this one core and optimize this based on what everything you've learned about CUDA? Why don't we take this core that can process 8 pixels at a time and make 16 of those, right? So now you have 16 cores, each processing 8 pixels each, giving it 128 ALUs. So now you can have 16 simultaneous instruction streams between different instruction streams, or running 8 pixels each, or running the same instructions with 8 pixels each. So you now have essentially, if we were to use CUDA terms, 16 SMs and 16 times 8 cores, if you think of it in CUDA. So if we were to think of this in terms of fragments and primitives, because these are 16 independent pipelines, all doing 8 things each, some of them could be doing pixels, some of them could be doing fragments, others could be doing primitives. So essentially what that just to say is, we could be working on different data and different instructions as long as each pipeline, each core is working on 8 of each. Okay. Now, this is all well and good, right? Taking this, multiplying it by 16, it's all good. What are some of the problems that may not work very well with this? And I'm talking about very common ones. Yeah. Oh, you predicted my slides. So what about that? Like if you have something like this conditional shader code, where you have an if else, how does that work? And these slides may look familiar to you in terms of design. So we come here, let's say 3 of these are true, the rest are false. That's essentially going to lead to 3 of them executing, all the rest waiting. and then 3 of them rating, and all the rest executing, which is in terms of our ALUs, because now they're executing eight memory units at a time, right? The worst case scenario is when you have if I equals 1, if I equals 2, if I equals 3, where you essentially get 1 by 8 the performance. So branch prediction isn't great in this. So, and that is acceptable. That is acceptable to us because we are designing this to be not great at branch prediction, but rather be great at general performance. So simply processing doesn't imply single instruction. So single instruction multiple data processing doesn't imply the same instructions. Option 1 is what we discussed before with SSE and AES, where you have explicit vector instructions where everything works on that same data. The second way is if you use scalar instructions and implicit hardware vectorization, sort of like what we do with CUDA, where you have giant code, giant chips with a lot of ALUs and a lot of memory, but very simple instruction and decodes. So that way you can increase the parallelism. But there's another thing, not just branch prediction. Even if you accept that, okay, branch prediction is something you can live with, there are going to be stalls when you're going to try to reach that much memory from your GPUs. You're going to run into stalls. So in the gaming world, you're going to be reading textures, you're going to be reading primitives. That stall is going to happen and slow things down. So we've removed the fancy caches, the logic that avoid those stalls by being predictive. So how do we fix that? So let's add in a cache, because we said, we definitely need this. We want to avoid stalls. Let's add a little bit of cache, very small. So we're talking about 32 KB and 256 KB, along with a giant L3 cache, which is much used for communication. And then we can add a memory bandwidth between our RAM and our cores. Okay. So what's the next optimization? So we've gone from just the core that can run in parallel multiplied by 16 or n. You add in some cache so that it's better with data. But what's next? How can we help this even more? So in the graphics terms, we have a lot of fragments, right? And being able to avoid those stalls by interleaving fragments. And I've written this here, but who can tell me in terms of CUDA what this means? No, anyone of you. Sorry? Yeah, so it will be scheduling words, right? So this is caused by memory, correct? So when a stall happens, you want it to be ready to switch it out and go to something else. So again, this diagram may feel similar to what you've seen before. So let's say we have in this chart, we have time on going top to bottom. We have one core, and then we have the 8 fragments that it can execute. But if we have 4 cores, look at this. Look at this context here, and look at this context. What's the difference? The difference is that these are independent contexts. So instead of storing one context from the entire core, now you can store 4 contexts. You're not changing how many execution units are. You're not changing the air rules. What you're changing is how the memory is arranged. You're not multiplying them. You're dividing up stuff so that each context is smaller, but now you have 4 contexts. Okay. So that is what we can do is, if the first set of 8 was supposed to hit a stall, because our second thing also have a context on the chip, we can switch it out very easily. And now because we're executing the same instructions, that's going to hit a stall as well. And then when that hits the stall, you get the next one. When this hits the stall, you get the next one. When this hits the stall, you come back to the first. So, exactly. So if you look at this diagram, instead of having uh, one pointer per A and B, which means if you wanted to switch that context out, you have to write this pointer to global memory, then load something else from global memory, which is very, very expensive. It's kind of pointless. Whereas if you do this, yes, the amount of data you can store in the context is much smaller, 4 times as small as our diagram, but now you can have four executions, four contexts, which are essentially free to switch out because all of this is cached. But the instructions are the same because you're executing it on the same data. So you see fragments 1 to 32, yes. If there were different instructions, then it would have to execute on a different code. Any other questions on this? Go ahead, man. Mhm. Yeah, so essentially there are schedulers on the GPU, right? That can not only take one kernel and how many blocks and threads it's scheduling, but can simultaneously take all the OpenGL calls, all the Vulkan calls that the computer is making in other parts. Like basically displaying this is stuff the GPU is doing. So it's taking all of that, making sure the scheduler is fine, and giving all the cores the right work to do. And then that's why if you have played games at ultimate settings and things like that, that's why it would slow down because the GPU has to still do the work. It can't skip the work because it's been ordered to do the work. But now it can't schedule everything at the same time, so it has to slow down. Any other questions? Great. So what does this concept remind you of in CUDA? Award. This is a voice of CUDA. So you're seeing, as I'm telling you more about how we do the GPU design, you're seeing how each of these things maps to some concept in CUDA, where in this diagram we have 8 threads being awarded. In CUDA we have 30 threads being awarded. And the context switching is similar and things like that. So, and I'll move on so that I can get to more points about that. So this bandwidth, essentially, this time to execute these instructions is essentially the throughput we get. Because we don't have to wait for all of this, and this space here where the stall is filled up by other threads and other memory, it runs much faster. Whereas if we didn't have the work that could be easily switched out, we would have to do all of one, then start two here, do all of two, then start three, do all of three, then four. So we are essentially getting sequential. Whereas now we can run them to interleave so that the context switching is much faster. So essentially, why stop? Why stop at 4 contexts? Just like our previous questions around 4, why stop at 2 or 4 or 8? Why don't we just make a giant pool of context storage, right? Which can store a lot of small context. So you have 8 here, you could do 12, you could do 4, you do what you want with it. It's general memory that you can arrange however you want. So an example chip here, this is CIS 565G, okay, based on what we've just talked about. So this has 16 ports, and we use the term 4 ports in house. Each port has one special port component. They have 8 images, so that it is 128 ports. Because you have 16 ports, you can have 16 instruction streams. You can't have 128 because each of these ports can only have one instruction stream, but different ports can have different instruction streams. So you can have up to 64 or 216 simultaneously. And then because each port can have 4 contacts, right? You can switch things out. You can have 64 functions, but intermediate instructions. So you're running 64 streams at the same time on your GPU. Even though they're not running at the same time, they're executing at the same time. For example, if the simple squad is and all of this means you can run 512 fragments at the same time. How? You have 128 ports times 4 contacts for each port, that's 512. And 512 fragments is 256 gigaflops at 1 gigahertz speed. Why 256? Because of the assumed flow of 4 clock cycles for certain point operation. That's 200. So here we've essentially designed or gone through how computer architecture has evolved to design. So let's compare them. GPU versus CPU and their memory. So here we have a CPU. Okay. So we have many gigabytes of RAM. Your speed is much lower for DDR3 RAM, so you only getting about 20. You have a giant SD stack, and then you have these cores that can do many things. Compare that to a GPU, where you have this giant memory bandwidth, because you have more compute, you want to bigger bandwidth as well to be able to read that. You probably have a smaller memory, although that's not exactly true nowadays. Nowadays, you can have more GPU RAM than CPU RAM if you want to. You have a smaller LP, much smaller than what LP is here. But then you have all of these many execution units with your execution partner that allow you to switch things out when you need. So that's why you need a much bigger bandwidth here, so that your performance here that you built up in your code is not limited by the bandwidth. So now let's do a thought experiment here. Again, some math and some hypothetical handling. So let's say we have to do a vector multiplication. A times b equals c. Let's assume there are millions of elements. Okay? So the order of operations is going to be load A, load B, multiply, and store. Everybody with me in this experiment? Okay. So the 3 operations, they're 12 by 3 for every multiplication. Okay, you have 3 memory operations for every multiplication. An older GTX 480 could do 480 multiplications per clock cycle. Okay, so that means if you wanted to get this advertised bandwidth of 177 gigabytes per second on a GTX 480, you would need, this is the advertised, right? To get this performance and to fill up all the cores, you would need 0.5 terabytes per second in that, which is basically possible. So you only get about 2% efficiency, but it's still 8 times faster. What do we call this kind of problem? I mentioned it at the start of the class. So then I failed without walking through down the entire slide. We have lots of memory that we want to do one simple operation, multiply. What we are saying is that the GPU bandwidth is nowhere close to good enough to fill up all the cores in our GPU. Right? To fill up our entire GPU and read all the millions of elements and multiply the elements and then store them back, you would need about 7.5 terabytes of speed, which we don't have. Now, the 7.5 terabytes of speed we don't have, but we do have 177 gigabytes. That by itself is 8 times faster than a CPU, which is good. But if you look at it in terms of total efficiency, it's only 2% efficient. So what is this kind of a problem called in parallel programming of CUDA computing? Good, man. Yeah, memory constrained or bandwidth limited. So what we are saying here in this problem is that a simple operation like vector multiplication, the limit is how fast we can read and write memory rather than how fast we can do the computation. So that's why it's bandwidth limited. The more bandwidth you can have, the more speed you're going to get. But there are other ways to optimize it so that you can change the algorithm to not be compute limited with bandwidth limited, just like how we did with our matrix multiplier earlier. So you're coming to the end. So what's in a GPU actually, or what is the GPU from the traditional GPU standpoint rather than from the CUDA standpoint? You have a bunch of CUDA code. In CUDA we call it CUDA code. You have a bunch of structure memory. In CUDA we can call it register, shared memory, etc., which is accessible to all the codes there. You have some fixed function elements. So these are your rasterizer, your blending, video decode. If I can extend, the probability. Maybe one day we'll have a Bitcoin code, a crypto code. I think we get disabled crypto code. Maybe one day you have a crypto code. And then you have a word distributor or a scheduler, which could either be hardware or software. So what we are seeing is there's a huge advantage to having all of these programmable cores to increase performance, but you're always going to need some level of fixed function programming, which doesn't need to be software controlled. It's faster on the GPU. And then you have a scheduler along with some memory. So in summary, what we've essentially done coming from one of the first slides, which was the CPU fetch, decode, execute memory, right? Using those 5 simple steps, we expanded it to have multiple pipelines. We discussed data parallelism, but now coming to the CPU, what we've essentially done is take the giant cores with complex logic, strip it down, make the cores themselves much smaller, and able to run in parallel. We do that by adding context within the chip and also adding the ability to share some information between those contexts. Lastly, we add the ability to switch those contexts out so that we avoid stalls by context switching between various threads on the same core. So if I go back, So we discussed that this is a what, right? And then in this line, we said there's 128 kilobytes of storage that you can use anywhere. What does this remind you of in terms of CUDA stuff? Yeah? You can partition it into blocks. What else? What other things about blocks? What is this remind you as a code in CUDA? It reminds you of an FM. Right? You have a bunch of cores, and then you have some memory and stuff to use. So this reminds you of an FM. What are some properties of an FM? Based on for scheduling blocks and things like that. So one thing we discussed is a block will always run on the same account, right? So the reason for that is because of that shared memory that we use, that's going to live here. If the shared memory lives in part of this, you can't have a group of threads executing in another SM because they don't have hardware access to this pool of shared memory. So that's why all the threads in the block will always run on the same SM. Some of the things, so we already discussed about what, how this is essentially the concept of what. Synchronization is also happening here. This memory is also used for synchronization. Your sync operation, that's happening there. So that's why, as we've seen graphics GPUs evolve, which is what we walked through, that has directly inspired how CUDA is CUDA, the architecture on the GPU is, and how it works. So it's still very much based on the fundamentals of having massive data, very small cores, and then being able to switch context between them for workloads. Yeah. So the raster is not used for changing this at all. That raster is there's no way for CUDA necessarily to follow raster. But when you do OpenGL draw or whatever the command is involving, that's essentially initializing the rasterizer. The rasterizer is going to access this memory for sure, but it's not something we could program like we program CUDA kernels. When CUDA kernels run, they're running for in the shadow in terms of contents of the raster. And that's why the rasterizer is faster. If you were to write a rasterizer, which was a project in this class, and if you're interested, you can definitely do it again. Your CUDA-based rasterizer is going to be much lower than the fixed function rasterizer because its fixed function is going to be much faster. Yeah, that's it for today's class. I will take any questions or we can leave 35 minutes early. Yeah. So the scheduler is run somewhere. It's an instruction, so we do a text input. But threads probably add like a flag in one of these contexts. No, you remember it's a generally they probably add something else. And then each ALU is probably adding a counter so that once the sync thread confirms that all the threads are adding something to it, it can then release the lock. Any other questions? Well, thank you so much for attending. So this was definitely more of a background of how we got to GPUs. And then in the next class, we take up more advanced CUDA stuff and how we can get into more of the performance stuff and understand how we write better CUDA programs. No, don't worry. Just get it.
I think it will allow me to register for a course that is in conflict with this course. I'm completing the final 9/11, the final translation. It overlaps the first 35 minutes of the Monday lecture.
Okay.
I've done it with other things. Well, I don't know about the final 9/11.
Have you finished with that?
I need to fill out the section 3.
No, I think you just have a time factor, right?
Yeah.
Are you able to register for the course?
The way it mentions voting of next voting allows me to shift and bring up. So I might have to drop the temporary settings for to get back.
All right. Let me know what.
And just for the homework, I'm taking it down. I wonder what the expected time range should be for part 1.
What do you do?
100 to 1000. I mean, after some optimization, it's about 7, 8. Is that too low?
You mean less than 1 FPS?
7 or 8.
7 or 8.
7, 8 for part 1. That's
7 or 8. You know, is CUDA Boy 7 or 8 frames per second for the live version? Yeah. And that's a desktop. Essentially the moon lab. Oh, the laptop. Yeah, it seems like anything. To be determined. Oh, definitely. I don't go to. We will do best in the December. So like 14, 15, whatever the Mondays that I'm at. I know every class has something.
Updating the videos to text. I'm just changing like 1 minus 9.
Yeah, make sure you note it in your pull request so that when we are opening it for grading, we see that note and we make sure not to dock you for an extra.
So I just edit my previous because I'm
Yeah, if you go into pull request, you can edit the message.
yeah.
Just edit that message to let us know that you committed that change, and then we'll just getting upfront about it.
So don't count. So that don't count the polls.
So I'm going to like the naive usually run on my standard equals. If I let it run for a while, it's going to be it also starts blowing.
Do you want to? Did you change your parameters then, try?
No.
Yeah, you might want to change your parameters.
I was just wondering if like the void control is just picking up.
Yeah, that's essentially what happens, right? So you have multiple boys and they're all influencing each other, and eventually they'll start moving in one. Like you
once
probably
you fill up the space with so
So it's sort of like you throw a rock in a pond, it creates waves, but eventually it all melts out. So sort of like that, where they all influence each other, and then eventually they can start moving in the same direction.
Also, like you said that increasing the number of shots is not increasing the performance, but I mean,
No. I did not say that.
oh,
I said depending on your GPU and your implementation, changing the number of threads per block, which means changing the number of blocks, can have different performance impacts. So, did you lower it? I lowered it. Oh. Always. From your perspective, you don't see it. No, it's always. Because it's like the first time you're like, oh my god, this is not working. How do I get this to work?
Yeah.
Good. She's just even I haven't had much interaction with her. She's standard executive assistant kind of person to sometimes. But I have a new problem. My Zoom doesn't want to show me how to end the call.
Oh, you got a full?
No?
Oh, maybe if you hit a bunch of things.
No, last time when I did the full screen, it did something. I'm essentially trying to play the engine for that button.
Yeah. Not a lot of reading.
Yeah. Yeah. Mm-hmm.
So I just have a 16 stories.
Mhm.
There's four to get one. This is recording. So after that, I don't know.
So you remember how we had the what? Because now we have 4 contexts in each core. Each core can run 4 interleaved tuples. It's the same instruction, but 4 interleaved because it's a swap device. They cannot have the same cycle, but they're easy to switch up. Yeah. So that's how you get 16 times 4, 64. You get 512 concrete cells. That's right, because you have 124 times 4 contacts per core. No. Yeah, you can count 64 times 8 or 8. I like to count times 120 times 4. Oh, yeah, that makes sense. Okay. Mhm. So you use the debugger, right? You essentially can't do open source debugger. Sort of like that. I mean, there probably is, and you can do it, but it's not as mature and not as easy. You thought NVIDIA was difficult, OpenGL is like so like. So it's more about the maturity of the tools, maturity of the documentation, the community around it, who answer questions on Google and Stack Overflow and stuff. So all of that implies that CUDA has had more momentum, they've had better drivers, better support. Whereas if you go to OpenCL, Intel is going to have one version. NVIDIA is going to have another version. Sort of like OpenGL back in the day, Some people had OpenGL 3, some people had OpenGL 4 and all that. So that all of that gets avoided if I have one CUDA version that I'm controlling. That's all? Yeah. All right. Thanks. Okay. No, I'm good. Okay. Mhm. Yes. Each technically each core has a certain number of resistors, but yeah.
So amount of total amount of space and like say you had
Yeah. So one second. Let me put them all together. Let me keep running the details for the problem.